Well, welcome to this online revision session for AQA FP3, in which we're going to look at the June 2010 question 5 on Mclaurin expansions and limits. You can see this question comes in three parts. The first part, A, we're just going to use the result of cos x as an expansion. It's given in the formula booklet to work out cos 4x. Second part, we will use Mclaurin's theorem to actually determine the expansion of ln of 2 minus e to the x. And then finally, we'll bring those two results together to find the limit of this particular expression as x tends to 0. So, part A, very much straightforward bookwork here. You know the expansion for cos x. If you don't know it, you can look it up in the formula booklet. And you can see here that if we want the cosine of 4x, all we need to do is substitute 4x in place of x in the expansion. And we want the first three terms up to x to the power of 4. So we're going to get 1 minus 4x squared over 2 factorial plus 4x to the 4th over 2 factorial, sorry, 3 factorial, 4 factorial, get it right at the moment, 4 factorial. And that obviously continues. And so if we then simplify this, we will get 1 over, and then notice I put the 4x in brackets to remind us that we are squaring the whole part of that, so that becomes 16x squared divided by the 2 factorial will just give us 8x squared. And similarly, we got 4 to the power of 4. Well, we got 4 factorial, so one of those 4's will cancel, so we've only got 4 to the power of 3, and 4 to the power of 3 is 64, divided by 3 factorial. Well, there's a 2 in there, so that will give us a 32, and leaves us with just the 3 on the bottom there, and that's the x to the power of 4. Okay, well, there's only 2 marks for that part, so it's basically using the correct method here, substituting into the expansion of cos x, and then simplifying it down to the correct solution gives you your accuracy mark for the second one. Now in this part, we're being asked firstly to find the first, second and third differentials of y equals ln 2 minus e to the x. So, find dy by dx. We know that the differential of the log function is 1 over, but then we've got to use the chain rule to differentiate the 2 minus e to the x. So that will give us minus e to the x. So we end up with minus e to the x over 2 minus e to the x. So that's the first part done. Then to get the second differential, we now have a quotient, so we've got to use the quotient rule in order to determine this differential. So the quotient rule says differentiate the top, which becomes minus e to the x, and multiply by the bottom, and then we differentiate the bottom, which is minus e to the x, and multiply by the top, which is also minus e to the x, but we have to then also remember that it's minus this second part, so we've got a minus with a minus with a minus, so overall the whole thing will be minus. Okay, And then on the bottom, we're then going to get the 2 minus e to the x, and that now has to be squared. Now, bearing in mind that we've got to, in a moment, find the third differential, it's probably sensible at this point to try to actually simplify this. And we can see we've got a minus e to the x times a minus e to the x gives us a plus e to the x squared. And we've got a minus e to the x squared here. So those will disappear, cancel out. And we're just left with minus 2 e to the x on top over the 2 minus e to the x all squared. To get the third differential then, we're going to have to differentiate once more. So again, it's an application of the quotient rule. We think. So I'll just find out. Yep. Okay. So if we do this, what are we going to get? Well, we differentiate the top. So that's going to give us minus 2e to the x again, and multiply by the bottom. And then we differentiate the bottom, so that becomes 2 times 2 minus e to the x. But then we got to multiply by the differential of the e to the minus e to the x, which gives you minus e to the x. So that's another e to the x here. And then we got to multiply by the 2e to the x on the top. And then checking all the negative signs, we got a negative to begin with, and then a negative when we did the differential here, and a negative from here. So overall the whole thing will be negative. And the bottom is then the squared again, so we now get 2 minus e to the x to the power of 4. And you note it says you can leave it unsimplified, so that answer will do just fine at that point. So you can see we've got 6 marks allocated to this. So for using the chain rule, you'll get a method mark, and then a correct answer will give you a mark. Next part, using the quotient rule, you'll get a mark, and again obtaining the correct answer, you will get a mark. And then finally a method mark for knowing what to do in this last part, and an accuracy mark will come in here. Okay, then in part 2 we've now got to use Mclaurin's theorem to find the expansion of ln. So each of these differentials and the function itself need to be evaluated at 0. So we need to firstly find out what is y when x is 0, and the answer to that is, well, it's ln of 2 minus e to the 0. Well, e to the 0 is 1, 2 minus 1 is 1, ln of 1 is 0. Similarly then, if we do y dashed or dy by dx at 0, you can see we've got a lot of e to the x. We know e to the 0 is 1, so that's minus 1 over 2 minus another 1, so that will give us minus 1 over 1, so that's negative 1. The second differential at 0, well, we can see we're going to have a lot of e to the noughts, which are 1, so you've got minus 1 times 1 at the end. We've got 2 minus 1, which is 1, times another 1, and that's a minus 1. So we've got minus 2. Might make more sense to look at this one, wouldn't it? So it's minus 2 over 2 squared, which is, sorry, over 1 squared, because 2 minus 1 is 1. So it's minus 2 over 1 squared, so that's just minus 2. And then finally, the third differential, evaluated at 0. Again, we've got 2 minus 1 when it's the e to the naught here, and that's 1 and that's 1. Here you've got 2 minus 1 squared, so that's just 1 and that's a 1. So we've got minus 2 minus 2 times 2 times 2. So that's minus 2 times 2 times 2 is 8. So all told, we've got minus 2 times a 1, and it's minus 2 times 1 times 2, so that's a minus 4. So overall we've got minus 6 on the top, or negative 6 on the top. The bottom works out to be 1 to the power of 4, so this is just negative 6. I'm very careful there just to keep the ones and all the negative signs in place. So now you can use your Mclaurin's theorem to find the expansion. So we know the first value is y0, which is 0. Then we get the first differential at 0 times x, so that's minus 1 times x. The next one, we then get the second differential at 0, which is minus 2, divided by 2 factorial, multiplied by x squared. And then the third one will become the third differential at 0, which is negative 6, divided by 3 factorial times x cubed. And so if we then simplify that result, we get what's required, minus x squared, and the 6 and the 3 factorial disappear, so we get minus x cubed. And of course there would be other terms if we continued. And that part, again, there's just 2 marks, so we get a mark for identifying these values at 0, and then a continuation through an accuracy mark in obtaining the correct result. Well, finally, we get to the third part of the question where we're trying to find the limit of this expression. And of course we know the expansion for ln of 2 minus e to the x, and we've got an expansion for the cos 4x. So if we substitute those things in, we're going to have the limit as x tends to 0 of, and again we're going to have x times our ln function, so what have we got? We got x multiplied by minus x squared minus x cubed, and so on, over 1 minus, and then we're subtracting 1 minus 8x squared plus 32 over 3 x to the 4, and so on. So before we can take the limit, we need to then simplify. So again, we simplify that. What are we going to get? Well, on top we're then going to get minus x squared, minus x cubed minus x to the 4. And on the bottom, the 1's cancel and we end up with 8x squared, because it's subtracting that, minus the 32 over 3. Then before we can actually take the limit as x tends to 0, at the moment everything on the top would become 0 and the bottom would become 0. So we can see the first term on the top is x squared, and the first term on the bottom is also x squared. So if we divide through top and bottom by x squared, that will sort it out for us. And so the top will become minus 1 minus x squared over 8 minus 32 over 3 x squared, and so on. And so now we can state the limit, because as x tends to 0, everything on the top disappears apart from the negative 1, and everything on the bottom disappears apart from the 8. And so we're left with negative 1 over 8 as our limit. So again, initially substituting in the terms that we've got here will give us a method mark. And then for identifying the process by which we can take the limit by dividing through by the x squared, and then finally an accuracy mark for obtaining the correct limit at the end. Well, hopefully you found that solution helpful. For more work to support your revision, please go to the Further Maths Support Programme website.